talk more about substitution and elimination reactions. Now we're going to talk about, this is super cool, we're going to talk about a marker here. I always forget to get my marker out before I begin. SN1, right? No longer SN2, and E1 reactions, okay? So let's figure out why these reactions are called that. So look at this following reaction. Consider this following reaction. So can you see we have a tertiary alkyl halide, right? It's tertiary. And we learned in a previous conversation that SN2 substitution reaction is not possible with tertiaries, right? So here's what we get. If we take a tertiary alkyl halide such as this, and we put it in ethanol, right? Then we get both a substitution product and an elimination product. Why is that? All right. Furthermore, we find that it follows first order kinetics, and that is that the rate is not dependent on two things, right? So in SN2 reactions, we found that the rate was dependent on the substrate, the concentration of the substrate, and also the nucleophile. Remember that? Okay. That was an SN2 reaction, but in an SN1 reaction, it's not dependent on the nucleophile, just the substrate. So why is that? All right, so the reason that is because let me go to a red marker, the leaving group leaves on its own. Yes, this is very intuitive. This is going to fit in your head very nicely. It leaves on its own. Why does it leave on its own? Well, first of all, there's nothing pushing it off, right? Because this is too crowded. So you can't get a nucleophile in there to push it off, right? That doesn't happen because it's too crowded, right? So the leaving group leaves on its own, and it can because it leaves behind a tertiary carbocation. Tertiary carbocation. You see it here? Look at that, a tertiary carbocation. And we know because of hyperconjugation that this carbocation, that electron-poor carbon, is stabilized. Right, so this is a relatively stable intermediate. Okay, it's not great. It's pretty reactive, but it's stable enough to actually happen. Okay, so after the carbocation is formed, then you can see. All right, now if I've got ethanol, right now you can see. Okay, well this is now trigonal planar. It's trigonal planar, which means it's flat, which means that carbon's much more accessible, okay? It's flat, and so you get some kind of a nucleophile, which is a bit bulky, but it can get in there, right? Because this is planar, all right? So, that said, let's look through here. The substitution reaction of a tertiary substrate in alcohol solvent, like ethanol, proceeds through a two-step mechanism. We already discussed the first step, the loss of the leaving group, right? There's the loss of the leaving group. This guy goes off on its own. And then the ethanol comes in, right? And that's step 2. So here's step 1, and here's step 2, okay? Now, after step 2, by the way, you're left with an acid. And so this is technically step 3, but we don't consider it in the mechanism because it's just a proton transfer. Yes, hear that again. This is really technically a two-step mechanism, although I should say really, it's actually 3 steps, but the last step is just a proton transfer, and so we call it two-step, okay? This is called solvolysis because the nucleophile is the solvent, so it's like the cutting of the solvent. That's what solvolysis means, cutting, right? Lysis, cutting. So solvolysis is something we'll see a good bit. And you can see why. If we have some kind of a polar solvent and we have a leaving group that leaves on its own very nicely because this is stable on its own and the carbocation is stable, well then all of a sudden, if you've got a polar solvent, boom, right? Okay, so this is not unusual. So let's look at the energy diagram for this. The highest energy transition state, right? Remember the transition state is the difference between, right? That's the activation energy, right? So the highest energy transition state in SN1 is for the formation of the carbocation intermediate. So this is the least stable of all of the things that we have going on. The The least stable is when the leaving group is leaving on its own, okay? Now, after it's gone, we have a tertiary carbocation, right, which is trigonoplanar. And then we have nucleophilic attack, which raises its energy level just a little bit because you have the interference of some incoming electrons and electron groups over here, okay? That's the nucleophilic attack. Once it comes in, we go back to a tetrahedral intermediate. Tetrahedral. This is trigonoplanar, right? Trigonal. Can you read my writing? Trigonoplanar. This is tetrahedral, right? That's also tetrahedral. Tetrahedral. Okay? So we have a trigonoplanar intermediate. Then we go back to a tetrahedral intermediate, and then we get proton transfer. And after this goes from, this is essentially an acid-base reaction. I think you recognize that. Okay? So since the highest energy transition state is this formation right here, that is the rate determining step. This step here is the rate determining step. Okay, since the formation of the carbocation requires only ionization of the substrate, the rate of its formation depends on the substrate. Yeah, the rate of the whole thing depends on the substrate because this is the slow step. So it's first order kinetics, right? And therefore we call this SN1 because it depends on the concentration of only one thing. That is the substrate. All right. So now let's talk about this in general terms. In general terms, we have a leaving group. Okay, this is just like what we saw before, but now we're generalizing it. Leaving group minus leaving group goes on its own, right? Now the leaving group can come back in. So this is if the leaving group comes back in, this is an equilibrium, right? It's just backwards reaction. Okay. Now, but if we have a good nucleophile that's not a good leaving group, nucleophile comes in, boom, and then you get the tetrahedral product. Okay? Remember that when the nucleophile is a neutral species, such as an alcohol, there's going to be a proton transfer at the end, right? So as we've drawn it here, we've drawn it as a negative nucleophile, but if it were, say, ethanol or water instead, right, then in the end, because this is neutral, you see that? Then once we get there, you would have had that, which is an acid, right? And so you'd have some kind of a base coming in to do a proton transfer. That plus really goes with the oxygen. Sorry, the plus goes with the oxygen. Form charge does, okay? So, but let me get rid of that and say, in general terms, get rid of all that and say, in general terms, if we have a these are the two steps, right? Loss of a leaving group, entrance of a nucleophile. Okay? Now the elimination reacts just the same, very same first step, loss of the leaving group, right? Formation of a tetrahedral carbocation. Now in this case, we're going to consider one of the hydrogens that's right here, all right? If you have a base in solution, right? So in this case, ethanol is acting as a base. The base comes in, right, and takes that proton. The electrons here go there to make a double bond. All right. So here, ethanol is serving as a base, not as a nucleophile. You can see, and I've called to your attention in previous conversations, that bases and nucleophiles have some very similar properties. Now, just by definition of what we're calling them, right? Oftentimes, bases have a lone pair of electrons and a negative charge. Nucleophiles can have a lone pair of electrons and a negative charge. So we draw them like this, though, to call attention to what they're actually doing. So a base abstracts a proton, right? That's what a base does. It takes away a proton. A nucleophile, though, attacks a nucleus, right? So it's useful, very useful to you as you're getting used to this, to think of these in two different terms. It's very useful to use in general terms because it reminds your eyes what's going on here, right? A base is going to be abstracting a proton. All right, so here in this case, ethanol is serving as a base and not as a nucleophile because it deprotonates the carbocation and it forms an alkene in its wake, just like the formation of the alkene that we saw in E2 mechanisms. Oops, lost my place. Where was I? Okay, so like SN1 and like SN1, E1 is also unimolecular because this is the slow step. right? That's you can imagine what the energy diagram of that would look like. It would look almost identical to the one we saw with substitution. And my feeling is it'll fit nicely in here. Here's the energy diagram. The rate of E1 is the same as SN1 in both cases because the rate determining step is the formation of a current. This step here looks identical to the SN1, right? Because all you're doing is you're getting, boom, the leaving group leaves, and after it's gone, it's here. You can imagine what the transition state looks like. You should draw that. What does the transition state look like? To be a good test question. And then the second step, then it depends on, right? It depends on what the actual product is. Okay. All right. Hopefully that's a good overview of SN1 E1. It might be good to go back and watch a previous video or two on SN2 and E2. Compare these very nicely and cleanly in your head before you get too far down the path.